Instead of asking what kind of computation creates consciousness, Penrose asks what physical process in the universe is non-computable, and could the brain be using it? The answer, he believes, lies in the most mysterious and poorly understood corner of physics, the intersection of quantum mechanics and gravity. He proposes that the very act of consciousness is tied to the process by which the fuzzy, probabilistic world of quantum possibilities collapses into the single, concrete reality we experience. This isn't just a philosophical preference. It's a search for a physical mechanism that could explain the unique, non-algorithmic nature of human thought. This line of reasoning places Penrose at odds with the vast majority of neuroscientists and AI researchers. It suggests that the quest to build a conscious machine by simply writing more complex software is doomed to fail. If he is right, no algorithm, no matter how sophisticated, can ever achieve genuine understanding because it is playing a different game entirely. The brain isn't just processing information, it is tapping into the fundamental process of physical reality's creation. The search for consciousness, then, must leave the world of pure information and venture into the strange physical machinery operating at the quantum scale within our own neurons. The brain is to harness a non-computable quantum process. It needs a place for that process to occur. The conventional view of neurons, as simple on or off switches firing in a noisy, classical environment, just won't do. Quantum states are notoriously fragile. The slightest thermal vibration or interaction with the environment can destroy them in a process called decoherence. The warm, wet, and chaotic interior of a living cell seems like the last place one would expect to find delicate quantum effects at work. This is the warm, wet brain objection, and it is the single greatest challenge for any theory of quantum consciousness. A suitable location must be found that is somehow shielded from this environmental noise. This is where Stuart Hameroff, an anesthesiologist and consciousness researcher, enters the story. He proposed that the perfect candidates for hosting these quantum computations are the microtubules. These are tiny, cylindrical protein polymers that form the cytoskeleton, or structural scaffolding, of every cell, including neurons. For a long time, they were thought to be simple structural supports, like the girders in a building. But Hameroff argues they are far more sophisticated. He suggests they are information processing devices in their own right, acting as the nervous system within the neuron. Their hollow, crystalline structure and the materials they are made of, he claims, could create an environment isolated enough to protect quantum states from the chaos of the cell. Microtubules are built from small, peanut-shaped proteins called tubulin. Each tubulin protein can switch between at least two different shapes, driven by the location of tiny quantum particles within it, known as electrons. According to the theory developed by Penrose and Hameroff, orchestrated objective reduction, or Orch-OR, these tubulin proteins can enter a quantum superposition, existing in both shapes at once. Furthermore, they propose that these individual superpositions can link up, becoming quantumly entangled with their neighbors along the microtubule. This would create a large coherent quantum state, a form of quantum computation, unfolding within the very skeleton of the neuron, shielded from the noisy cellular environment. This is a radical reimagining of cellular biology. It elevates the microtubule from a passive structural element to the active computational core of the neuron.